Moving on to lesson 7, I want to apologize because my voice has been strained for quite some time. So I've tried to save it for this as much as possible, but I realized that I'm not talking as clearly as I normally would. So in continuing the electrophilic aromatic substitution reactions that we have seen, the next one that I want to cover is the nitration of benzene. Benzene in combination with fuming nitric acid and fuming sulfuric acid produces nitrobenzene, as you see right here. Yes, water is produced as well. What we care about is right here. So, exactly like we just saw in the other examples, we first have to form the electrophile. Fuming nitric acid and fuming sulfuric acid, this oxygen will come and grab the hydrogen there, making these electrons go back. Because sulfuric acid is, even though nitric acid is massively acidic, fuming sulfuric acid is a little bit even more acidic, which is crazy. And of course this is an equilibrium, which I did not write in, so I'll write that in now. And what we form is this crazy sort of intermediate, which leaves a positively charged, basically a water molecule over here. So these electrons move over here, and then the water molecule leaves, forming what we call a nitrosium ion. And this now becomes your electrophile. So now we go as we've seen before. These electrons come and grab that electrophile. Those electrons go out. Again, this form is also stabilized through resonance, just as we saw before. Some form of base comes and removes the hydrogen, electrons go back, and then we have an NO2. Just a note, because I saw some confusion on the base there, that base is not something that you add. That base is usually something like HSO4 minus, or it could be any type of solvent in other cases that you would have in here as well. So it's something that's inside the reaction mixture, it's not something that you're adding. Okay. You'll note that the sulfonation of benzene is very similar to that of the nitration of benzene. Sulfuric acid, it's fuming, is added with heat, making an SO3H substituent on a benzene ring. This is a reversible reaction, so you have to watch it. Basically, the reason why you use fuming sulfuric acid is that drives the reaction this way due to Le Chatelier's principle. One of the things you can note with the sulfonation of benzene, depending on who is writing the reaction, you may also see that SO3 is used in combination with H2SO4. That is the same thing, because SO3, as we'll see in just a second, is also a byproduct sort of this formation of the electrophile. Okay, so here we have two sulfuric acid molecules, and because I didn't note this earlier, yes, that's what sulfuric acid looks like, that's what its Lewis dot structure looks like. This is what nitric acid would look like. It has a positive negative charge in there. Okay, so here one sulfuric acid molecule, comes and basically grabs the hydrogen from another one. Electrons go back to that oxygen, and you have an HSO4, that's from this guy. And then you have this guy that has two hydrogens on that oxygen. These electrons leave, giving you the water molecule, but more importantly forming this electrophile. As I was saying, you could also add SO3H, because SO3 plus H3O plus will basically form that same electrophile. Then again, we come to the same type of mechanism, where benzene comes and takes comes and donates electrons to the sulfur. A base then comes and removes the hydrogen, electrons go back, and again, you end up with an EAS reaction that's completed there. Okay. Next, let's talk about a Friedel-Crafts acylation reaction. This can be formed with either an acyl chloride or an anhydride. We use AlCl3 as sort of our conjugate here, our reagent here, followed by water. I'll talk about the water in just a second. But first we have to form the electrophile. So kind of similar to what we saw with FeBr3 or FeCl3, the chlorine goes and donates electrons to the aluminum because the aluminum chloride is acting as a Lewis acid here. You form a positive negative charge on that chlorine aluminum, and that breaks this bond, forming this as your electrophile. Part of the reason why this is even possible is because it's stabilized through resonance to also include an RCO with a positive charge on the oxygen. So otherwise, this might not really exist so easily. Also produces AlCl4 minus. Then again, your benzene is going to come and donates electrons to the electrophile. A base comes, removes the hydrogen, and bam, there you go. Now you actually usually use excess AlCl3 in these reactions because aluminum really likes to react with oxygen, or better yet, just be close to it. So you are adding extra because you may have a lot of the aluminum tied up on the oxygen. And then what the water is used for is to flush out the AlCl3. So by giving the AlCl3 or aluminum Cl4, either one, some water, it will basically wash out all of the aluminum from this reaction. Okay, now you could also do this, as I said, with an anhydride. And how that works is, well, that oxygen, as I said, likes to donate electrons to the aluminum. And that forms this really crazy, weird transition state where we have electrons come down from the one oxygen, electrons go over from another, and basically that's going to create this as an Rc+, which is the same thing we see up here, and that goes back and forth here. Okay, so let me show you where the Rc+ comes from. This R, this carbon, that oxygen. See how these electrons go down here? This bond breaks, so the rest of that is not even in play anymore. And basically that's what you end up with. And that creates your electrophile. This does waste sort of an equivalent of R if you want to consider it that way. So you have to be careful with that a little bit as far as price is concerned. Okay, and finally we have the thing that I see most often used incorrectly of these reactions. I'll explain that in just a minute. In the same way you could have an acyl chloride, you could actually have an alkyl halide, just RCl, whatever the R group is, just any alkyl chain, with AlCl3 to give you that R group on the benzene. Works very similarly. The chlorine comes and donates electrons to the aluminum. That makes this guy leave, and you form a carbocation. That carbocation becomes the electrophile. Electrons get donated. We have the same type of format as we've seen over and over now. The problem with this reaction, and the reason why it's most commonly misused, as far as what I've seen at least, is this carbocation forming. If you recall, carbocations will rearrange to become the most stable as they possibly can. So, for example, let me go one at a time here. Say you have a secondary alkyl chloride. You add AlCl3, this forms a carbocation. But a methyl shift will happen in order to change the electrophile so that it is the most stable as possible. So that means that your carbocation will have a positive charge as a tertiary carbocation, not as the secondary that you may have intended. Why does it do this? If it has enough lifetime, it does this because it's lower energy. Because it can. Anytime you form a carbocation, the same thing can happen. Say if you have a primary alkyl chloride in the presence of AlCl3, positive charge is a primary carbocation, that methyl shift can happen again. You'll end up with a secondary carbocation. If we have a reaction like this with AlCl3, you get a positive charge here on the end, that hydrogen will shift. So a hydride shift is also possible, giving you a benzylic carbocation. The only case that this will not really be affected, or not really affect your reaction so much, is when you start off with a tertiary or most stable form of the carbocation anyway, like right here. That's not going to rearrange, giving you the electrophile that you actually want and allowing that to attach. So just to be clear, wherever your positive charge is after the rearrangement is where the electrophile will serve as an attachment point. So that means that this would give you a product like that, even though you started with a secondary alkyl halide. And this guy would likely give you a product like that, even though you started with a primary alkyl halide, etc., etc. Okay, thank you very much.